All right, so this is the beginning of chapter 11 in pre-calculus. We're kind of skipping ahead, way ahead in the book because I want this whole unit to be about equations. We just spent some time in chapter 2 talking about equations and graphs of equations and how that relates geometry and algebra together. So, jumping ahead to chapter 11, we're going to spend some time looking at systems of equations. So the idea here now is instead of having a single equation with two variables and trying to graph it, finding points on the graph, i.e. solutions to that equation, instead of just that, we're going to have two equations with two variables and try to find solutions that satisfy both equations at the same time, which is a little bit harder to do. We'll also be looking at three equations with three variables. And sort of in general, you could have any number of equations with any number of variables. So we're going to start this off with a motivating example, which is a mixture problem. Many of you have probably done mixture problems in your previous math classes. So here's the problem. A biologist has a 20% salt solution and a 70% salt solution. As I was writing this, I realized that's probably unrealistic because water can only hold so much salt, and pretty sure you can't have salt water which is 70% salt. But just go with it, all right? The numbers don't really matter that much, so much as the idea. So we have two salt solutions. One is 20% and one is 70%. What we want is 10 milliliters of a 50% salt solution. So with 20 being less than 50 and 70 being more than 50, we should be able to mix these two solutions together in some ratio to produce 50% salt. And specifically, we want 10 milliliters of that. So the question is, how many milliliters of each of the two solutions that we have should we combine together to get exactly what we want? So we can solve this, of course, with algebra and setting up a system of equations. But before we do any equations, we've got to decide what our variables are, and we've got to label them very, very precisely. So we're going to have two variables here. One is the milliliters of the 20% salt solution. Let's do some color coding. So 20% salt solution will be in red here. And then the other variable is the milliliters of the 70% salt solution, which we'll put in purple. So with two variables, I need two names. I'm going to go with X and Y. You can pick A and B or any other two letters that seem to work for you, but I recommend X and Y. So let's have X be the milliliters of the 20% solution. So that is the red one here. And in particular, X is the milliliters, okay? A lot of times people make the mistake of just saying, let's have X be the 20% salt solution, without thinking about what the units are. How are you measuring the quantity of that solution? It's in milliliters. That's key, all right? So the other variable, Y, of course, will be the milliliters of the 70% solution. That's the purple one. So I can't stress how important it is. I can't stress enough how important it is to actually write this down. Okay, if you just sort of have this notion in your head but you never write it down, it is very easy to forget which one is which by the end of the problem because you're going to do a bunch of algebra. All right, so with that written down now, what we can do is start to think about this problem and write down relationships in the form of equations. So the first thing we might want to write down is that these milliliters, when we combine them together, need to add up to the desired quantity, which is 10 milliliters. So the first equation we can write down is that X plus Y has to add up to 10. That's pretty easy, okay? Because the quantity needs to be 10 milliliters total, right? We don't know exactly what it's going to be, whether it's going to be like 5 and 5 or 4 and 6 or 3 and 7 or whatever. We don't know what those milliliters are going to be. And I just picked integers, but obviously it could be, any number, 2.8 and whatever 10 minus 2.8 is, 7.2. So we've got that equation, And now the second equation has to be something to do with the salts, right? Like we need to make it so that the percentages balance out to 50. 50 is not exactly halfway between 20 and 70, right? It's kind of closer to 70 than it is to 20, right? It's 30 difference and then a 20% difference. So we just need to make sure that the amount of salt in the X milliliters plus the amount of salt in the Y milliliters is going to add up to the desired amount of salt. So the way we can do that is to remember that percentages, if you multiply a percentage by a quantity, that applies that percentage to the quantity and calculates a new quantity, like a smaller percentage. So multiplication is the key here. And the other thing to remember is that percentages can be written as decimals. So 20% is 0.2. And if I multiply that by the X milliliters, what I get is 20% of that X milliliters. That's the amount, that is the number of milliliters of that solution, which is going to be salt. The rest of it, I assume, is water. So there's 20% of X, and let's add that to 70% of Y. Okay, so the 20% of X plus the 70% of Y, that's adding the salts together. Now that needs to equal 50%, right? 0.5, but not just that. I don't just want to write 0.5 there, because 0.5 is a percentage. That's just 50%. What is it 50% of? The total, right? So it's 50% of the X plus Y, which is 10. So I'm going to put 10 in there. 50% of 10. So this is 0.5 times 10. All right. Those are the two equations that we can write down that are going to sort of describe this problem. Okay, and this is our system of equations that we want to attempt to solve. That's our system. Okay, two equations with two variables. The goal is to find, well, let's write down the goal here. The goal is to find X and Y values that satisfy both equations. Okay, so one thing you could do is guess and check, right? Guessing and checking is never a good way to solve equations, but with systems of equations, it's even worse, because now not only do you have to get lucky and satisfy one of the two equations, you have to get lucky twice and satisfy both equations, right? So so guessing and checking is exceedingly hard to do. We can be a little bit prudent about the way we guess. We know that these things have to add up to 10, so let's guess 5 and 5. All right, I'll just show you what it looks like to do a guess and check. Let's guess X equals 5 and Y equals 5. So now to check that, we would check our two equations. The first equation would become 5 plus 5 equals 10. That's true, so check. That checks out. Right? So we guessed something that satisfied the first equation. The second equation is going to be 0.2 times 5 plus 0.7 times 5 equals a half times 10. So that's going to be 5 here. Okay, 0.2 times 5 is 1, and 0.7 times 5 is 3.5. And so this gives us 4.5 equals 5. That is false. So, like I said, guess and check, not a good strategy. It's hard to do. But this is how, if you were given a pair of numbers, this is how you could check to see if it is a solution to the system. You have to take those numbers and stick them into both equations, and they both need to be true in order for this to be a solution. So, not a solution to the system. All right, there are two methods for solving this system that I'm going to go over. There's these two very general methods for solving systems of equations that I'm just going to demonstrate on this problem. I'll put it in a separate video because this is getting kind of long. But one method is called the substitution method, and the other one is called the addition method. So that's coming up next.